Morning, Shubh. For the last two sessions, we have been doing Gauss law, and let us make one more session for Gauss law and some examples. Today's class we will do again the case of finding intensity. This time I am taking the case of charged non-conducting sphere and to find intensity at different locations. Now, what is the difference between a conducting sphere and a non-conducting sphere? Remember, sphere means always filled with inside stuff, material is there. What is the difference between conducting sphere and non-conducting sphere in the case of charging? The difference is that in the case of conducting sphere, all the charge will be expelled onto the surface. Therefore, we have only surface distribution of charge. There we have used a surface charge density sigma, and it was the case last time we did it. Now, in the case of non-conducting sphere, when it is charged, it will be the case of volume distribution of charge. Right? No question of surface distribution of charge, it will be the volume distribution of charge. Now, here again, different cases are possible, like uniform distribution of charge and non-uniform distribution of charge. Now, the simplest case now we are taking is the case of charged non-conducting sphere, and it is uniformly charged. That is, the charge density, the charge by volume will be same at any given volume. Such case we are taking uniform distribution, uniform volume distribution of charge. Right. So remember, this kind of volume distributions are never possible in the case of conductors. Now here, this is again a volume distribution of charge. That is, a charge of capital Q is distributed in the volume distribution with a radius capital R. Therefore, here the terminology what is that refers to is the total charge, right? The total charge, I am taking it as capital Q, and what is the volume? The total volume of distribution. The total volume of distribution. Since R is the radius, I am taking the volume as 4/3 pi R cube. Pi R cubed is the volume. Therefore, what will be the charge density? Now, it is not linear or surface density, simply density, that is by volume. So now I am writing for charge density. Charge density, let me use a symbol rho, right? This is not P, friends, this is rho, is charge by volume 4/3 pi R cube, right? If I write 3 here, 4 pi R cube. This is what is the charge density, and we have told that this rho is constant everywhere. There may be other examples where this rho itself is variable. There also we will use the same 1, 2, 3 steps, but with the difference of that final calculus part. That is the only difference. We'll do that. When you come back, we'll do that, or else you can call me. You can call my teacher personally, and you can do that with a small hint from the teacher. Now, this is surface charge density, and I said that. And let rho be constant. That is what is the case of uniform volume distribution of charge. Now again, to find the intensity is our objective, but at which location? Remember, in the case of shell also we have taken 3 different locations. One point well inside the surface, inside the shell, inside the sphere, and one point on the surface, the other one is outside. We have given the results, and remember there inside the field was 0. Now let us take the same case of inside point, a point on the surface and a point outside the surface. Now the case 1 I am taking. What is that case 1? Case 1, intensity at a distance small r. distance small r such that the condition is small r less than capital R, that means that it is inside point, right? If small r is equal to capital R, it becomes surface point. Small r greater than capital R, it becomes outside point. Now, intensity at a distance small r, of course this R is from the center. Let me mention, that is from the center of this spherical distribution, right? From the center. Intensity finding, again the same case of Gaussian surface and everything, right? Now let us, as I have told you when we are doing the separate cases, let us draw the figure separately and show it. Now first here itself I show, for that I will be using some green color or red color I will use if it is visible to you, right? So now this is the point of observation. I call this as P1, which is inside the surface, and this is what is the distance said to be small r. It is right, small r, any symbol, D-A-R, any symbol, r from the center. Now the question is that intensity Gaussian surface. So now this is a sphere of radius small r. This is a sphere of radius small r. Capital R is the total radius, right? A bigger sphere, and then this small r is a smaller sphere within this one. Therefore, now I am writing to find intensity at P1, right? We imagine Gaussian surface. We imagine Gaussian surface as a sphere of radius small r. Radius small r. And once again the same case, dividing it to elements and considering one element drawing using Gauss law. Therefore now here we show, supposing again red color I am taking, this is a small element of the area on the surface of the sphere of radius this r. Again the same case, this is what is red color, ds bar. Is it okay? Or let me show bigger. This is what is ds bar. ds bar, red color, ds bar, and here itself I show this E bar. This is what is E bar. Because flux leaving or entering the surface always normal to the surface, right? Now here this E bar, ds bar, you can see that they are parallel. Once again, theta is equal to 0 degrees. Therefore now I am applying Gauss law, right? Using Gauss law. Using Gauss law for an element ds. What is that? We get integral E ds cos 0 degrees. Because at an element ds, let us remember E bar parallel to ds bar, which is shown in the figure, right? E ds is equal to, I will now write this as small q. Remember, symbols when we are using, let us be very, very cautious. There earlier I have put capital Q, the total charge which is distributed in the volume of 4/3 by R cube. I'm sorry, here also capital R cube, right? Yes. So this kind of small mistakes do happen, not small, but they happen to be the costliest mistakes. So capital Q is the total charge and capital R is the bigger radius, right? Now here, this small q is, or let me write, q by epsilon naught, where this small q is, yes, what is small q? Charge enclosed by the Gaussian surface. Charge enclosed by Gaussian surface, which is a sphere of radius r. Therefore, q is charge enclosed by sphere of radius small r. It is not capital Q, it is different from capital Q, and of course obviously the small q less than capital Q because it's a smaller volume, right? Therefore now this Q is equal to, yes, how much you write? Because already we have taken such charge per unit volume, right? Charge per unit volume into volume will give us the total charge. Therefore, this Q is the surface charge density times 4/3 pi small r cube. This is the definition. Let us use here. This is what is integral E, which is the same, and it is integral ds. E outside the operator, E integral ds is equal to, this Q is now nothing but, yes, rho by epsilon naught, and then this is 4/3 pi r cube. Right? Now let us, we know that what is this integral ds? Integral ds is the, yes, integral ds is the surface area of the Gaussian surface. Okay. Now, this integral ds is nothing but the surface area of this Gaussian surface. Therefore, it is 4 pi r square, right? 4 pi r square integral ds is the surface area of Gaussian surface. 4 pi r square. Now substitute the values, right? Now E is equal to, that is E times 4 pi small r square is, yes, what is that? Rho by 3 epsilon naught, rho by 3 epsilon naught 4 pi r cube, right? So final answer you will see r square r cube 4 pi. Therefore E is equal to rho by 3 epsilon naught times small r. Is it okay? E is equal to, yes, the expression E is equal to rho by 3 epsilon naught times small r. Rho, of course, as we said earlier, a uniform distribution, rho is constant, this is all constant. E is equal to rho by 3 epsilon naught or E proportional to R result we will get, right? Now the same expression, supposing if we substitute it for 4/3 pi r cube, suppose if I am substituting for 4/3 pi r cube also, then also you can write it in terms of both capital R and small r also, okay? Now E is equal to, now you can immediately see that for small r is equal to capital R. I said small r equal to capital R, it will be a point on the surface. Then it is simply small r becomes capital R. Is it not? Now I am writing. Because second case, which is a point on the surface, again we need not do all this part. Because remember, here Gaussian surface is a sphere of radius small r, where r is the distance. Now if I consider a point on the surface, the Gaussian surface is nothing bad. Yes. The whole bigger surface becomes the Gaussian surface. Therefore, now for the second part, I will simply make a mention and I will write the result. Now case 2 is to find intensity of field E on the surface or at the surface point. Surface point is not a good usage, a point on the surface. How do we get that? Now if you call this as equation 1, now here simply I will write as substitute small r is equal to capital R in equation 1. Is it not? That will give the direct result. Now you may logically think that, sir, if for the outside point, let us see. For outside point, what will be the case? Substituting of this small r equal to capital R, what will be the result? So this E is equal to, rho means, yes, capital Q by 4/3 pi r cube. This rho I am first writing. And then it is 3 epsilon naught is there, right? 3 epsilon naught is there, and this one is smaller, which is I have taken as capital R. So R cube R 3. Everything is gone. So what is that? E on the surface I am writing ES. Here this is for EI. I for inside point and S for surface point. ES is equal to how much you are getting? 1 by 4 pi epsilon naught is there. Yes, 1 by 4 pi epsilon naught is there. Yes, on the numerator Q is there and denominator R square is there. Right? Look at this result. I have inequality equation 2 which is on the surface. Look at this result. This result is similar to the one of, yes, conducting sphere also. Conducting sphere or shell we have taken, right? What was the result on the surface? The same 1 by 4 pi epsilon naught Q by R square was the result. So here also it is the same case. Now, what about a point outside the volume distribution? Now can you write it as, so put smaller equal to smaller? No, we cannot do it. Why? Because there, what is the difference that you get? Let us see. Now I'm writing for the case 3, a point outside, right? So to find E, remember this is equation 1. Here itself I will show the equation 2. On the surface is 1 upon 4 pi epsilon naught capital Q by R square. Capital Q by capital R square. Here in equation 1 it is small r, right? So now case 3 I will write to find E at an outside point. Outside point, then we cannot do that small r equal to capital R. No, that is not possible here. Now for that one more time, show the Gaussian surface. Show the Gaussian surface, which will be again a spherical symmetry is there. Therefore now to find this, see, this is what is the volume distribution as I have shown. This is all the volume distribution, right? Uniform distribution. Earlier we have considered the cases of a point inside and on the surface. Now here it is the point P. And then again the Gaussian surface. Here we get the Gaussian surface as a sphere of radius small r. Right? The radius of this Gaussian surface, because this is what is the distance small r. Again remember the small r taken from the center. So now this becomes a Gaussian surface. So for that Gaussian surface, what will be the case? Again an element, again the two cases of ds bar and E bar. ds bar and E bar, then what will be the result? E integral ds is equal to capital Q by epsilon naught this time. Why capital Q, you tell me? Because the Gaussian surface now encloses the total charge which is capital Q. In the case of a point inside, we have a smaller sphere of radius smaller, which is smaller sphere, and therefore that charge is lesser here in this first case. But now when it comes to the question of outside point, now you see the Gaussian surface is enclosing the total charge and therefore this becomes Q. So when you are doing the derivation, small letters, capital letters, it makes all the difference, and therefore please practice it well. Q by epsilon naught, therefore to find the result again this is what is E times 4 pi small r square is Q by epsilon naught. Therefore our final result, which is outside point EO, is equal to 1 by 4 pi epsilon naught Q by small r square. Again the same case of charged conducting sphere. Remember, outside point and surface, whatever results we got for charged conducting sphere, charged non-conducting sphere, results are one and the same. But there is a huge difference with respect to inside point you will find. In the case of charged conducting sphere or shell, inside the net, inside the field is always 0. No flux is present. Field 0 means flux is 0. Whereas in the case of non-conducting sphere, there is a field inside the sphere. Field present means flux is also present. So now flux is present inside and as well outside the sphere. In the case of conducting sphere, flux is present only outside the sphere. These are very simple things, is it not? Appears to be. Yes, of course they are. But this is how you will look at each and every small detailing, and you will make a mention of such your understanding through your observation. Once you know, in the classroom or now at least in the virtual class, when you watch the video, it is possible for you to watch this video twice or thrice. Second time also you watch, and second time you try to make more observation. Out of your observations, what are your picks regarding the concept? You write it. Sometimes it may be some very nonsensical thing that you have understood by some misconception. It's okay, it doesn't matter. But when you discuss with your teacher, that misconception will be rooted out. So listening to the classroom, learning will be finished only when you just communicate with your teacher regarding that concept. What was your understanding, what was your doubts, right? And sometimes my student may be better in giving our observation. You may find more information than me as well. So likewise, once the concept is over, learning is never over. It is the duty of the teacher is over, but when the duty of the teacher is over, there your duties and responsibilities begin. You practice and never forget to communicate with your teacher. Okay, go on doing like this. Now what I would like to do is that I would like to show all those results that we have derived so far, right? All the different cases and intensities, because this simple tabular column is what is a major tool for all types of examinations, problem solving, for board examination, 1 mark, 2 mark questions, for board examination, CET like examinations, whatnot. For everything, now with respect to intensity, numerical examples whenever you study, this is a simple tabular column I want you to do on your own, but this time I am showing. Latter parts, when any such things comes, you please make a tabular column, what are the different expressions and what is the meaning of each and every term that we have mentioned with right SI unit, right? Now let us see the tabular column and if possible, try to make 1 or 2 important additional points as well. Let us see that. Friends, remember, these are all the expressions that we have actually derived. No question of memory here. We have derived all these expressions. Each and every derivation a very popular 3 marks, 5 marks questions for board exam. And these results, this should be a kind of, when it is understanding, there is no question of memories or data. Understanding is completely a package. When you do this derivation and practice it, and as I have told, some periodic repetition into a small notebook, then certainly this will not be a problem with your memory. Now see all these expressions, intensity with different cases. In all such cases, E depending upon distance, is it not here also? Distance, there also. So it's all these cases except this one I am telling you, conducting sheet you forget. Remaining 1, 2, 3, 4, 5 that we have discussed, they're all non-uniform electric field. Non-uniform electric field, it can be in 2 ways, is it not? Uniform electric field, remember in the beginning, field is said to be uniform if its intensity is same both in magnitude and direction at each and every point. Supposing if direction is changing, though magnitude remains constant, direction changes, non-uniform. Same direction but magnitude changes, they are also non-uniform or both may be different in all such cases. Now here, 1, 2, 3, 4, 5, all these are certainly non-uniform magnetic fields with respect to both magnitude and direction. All these cases. Dipole, of course, distance changes and also the direction, because axial point, equatorial point, all these are at different points, right? All these are non-uniform, but now look at this. conducting sheet. And as I have told you, E proportional to 1 by R square, E proportional to 1 by R cube, E proportional to 1 by R square. There also you will see different cases, is it not? Graphs as well, try to plot the graphs. 1 or 2 graphs I have shown, requires you also try to solve them. Plot 1 or 2, if any doubts you can anyways call me. Now let us come to this particular result. Conducting sheet E is equal to sigma by 2 epsilon naught. Remember this was a case of conducting sheet. And you know the reason why, you know the reason of this number 2, the denominator, because flux on either side of the conducting sheet, either side of the conducting sheet, therefore we have taken 2 surfaces flat, 2 times epsilon naught. This you will see that independent. Now let us have a small 1 or 2 statements regarding this. Look at this expression particularly. This expression, what you find is, yes, it is. And also see the figure as well. Also see the figure as well. If this is what is the conducting sheet I have taken, long sheet, and suppose it is positively or negatively charged, and as usual it is uniform distribution throughout. Now supposing if there is a point P here, a point P1 at a distance say 10 centimeter, now I consider another point P2, another point P2 which is at a distance of 20 centimeters. Now in such cases, if you want, look at this expression sigma by 2 epsilon naught. Sigma is uniform distribution, a constant, epsilon naught a universal constant, independent of R. Independent of R. Therefore here the intensity is, if this is what is E bar, at P2 also it is same E bar. Of course, because direction is always normal to the sheet, we have told, right? For positive charge, away, negative charge towards, like that. So if this is what is E bar here, this is also E2. And therefore what you find here is, irrespective of the distance, the intensity is same at all points, which means that both magnitude and direction being same at each and every point, that's what is uniform electric field. Therefore, in the case of conducting sheet, E equal to sigma by 2 epsilon naught is a uniform electric field. Supposing if it is a non-conducting sheet, flux only on one side, therefore the answer will be sigma by epsilon naught. So conducting, when becomes non-conducting sheet, then this 2 will disappear, then the result is sigma by epsilon naught. In that case also it is a uniform electric field. Now here, if it is a conducting sheet, now on either side, if it is the one which I have shown upward field, downwards it will be what is the electric field that you observe, is it not? So either side it will be there in the case of conducting sheet, non-conducting sheet is this one. So these are the different cases that we have derived actually. Few more things we should also discuss, but not at this point of time. But still, if you are with hunger, if you are really interested to do, I will give you few cases. You try on your own. You try on your own your best, let it be good, better, best or bad, worse, anything. You try on these lines, the fundamentals which you apply them. You don't get it, no problem, you can contact your teacher at any time. Right. So 6, 1, 2, 3, 4, 5, 6 non-conducting sphere, all these results should be your permanent asset with you. If you are ready with these expressions, along with expressions of course, all these are vector quantities, how to draw those vectors is also an essential point, right? If you are ready with that, then beautiful examples we can do. Now, as I have told you, if you are interested, let me show 1 or 2 examples. As a homework, I will tell you. You try to do this, and if not, yes, you can definitely contact me, right? What are those cases which I am giving you as a homework, right? See here. We have seen the case of a line of charge. A line of charge which was linear. We have shown like this. And we have taken the case of long line, infinite length we have taken, extended on either side, lateral points or along a point along the conductor we have told. Now, if it is a finite length, what is the intensity at a lateral point? This is one thing, already I have done and told you. Supposing now what I do is that a conducting wire is bent in the form of a ring. This is a ring. This is not a disk, therefore let me show this is a ring, thin ring. Thin ring thickness is very very small as compared to the radius. Again the same, if Q is the total charge distributed on the wire and wire bent in the form of a ring of radius capital R or some any other symbol you want or you wish, right? This is the center. Now the point is that how this is placed here that I am showing you. Now supposing if this is what is the x-axis and y-axis, board is xy plane I have taken, board xy plane I have taken, but the ring is in xz plane, right? This is what is the orientation that I have shown, right? This is the plane of the ring, which is nothing but yz plane. This is yz plane for the ring. Then this is what is one line I have taken. Look at this line. This is what I have shown as the plane of the ring. Now this is one line that I have shown. This is passing through the center and perpendicular to the plane which we call axial line of the ring. So this is called axial line of the ring. So this is one such line that I have shown. This is line. And here only up to this ring, and this is passing to the center. Now let me take this O is the center, P is an axial point. Your choice, a radius, suppose capital R. This is P, an axial point at a distance, suppose smaller from the center. This is total charge capital Q. Now I want you to calculate what will be the intensity at this point P due to this charged ring. This will be one beautiful feast for you. You try different ways, not coming, you have to enjoy that moment when you are not getting anything. Don't worry. Afterwards you can speak to me. Supposing the same case, charged ring I have taken. Suppose next time, another example, you take the charged disc. This was a ring, and now this I have told you this entire thing is a disc. And the disc is charged, capital Q, again can be positive or negative. Suppose I have shown all the positive charge, this is a positively charged disc. Again the same case, this is what is axial line. Radius capital R, P is the axial point. You create the question. Same way, instead of ring, it is the case of disc which is charged. And let me tell you, it's again a conducting disc. So on either side you will have the flux, right? Here also you will have the flux on either side, the field on either side. So here, this is the point P. Now, what will be the solution? And before that, let me tell you, don't use Gauss law for this. Don't use Gauss law for this. Use only Coulombic force. Coulombic force, when you are using, the only thing is that you cut these conductors into small elements. This is one such element, and this element will have intensity at this point P, and it goes on. So don't use Gauss law here. Use only Coulombic force. I do expect a few calls after your trial and errors, right? Let me expect that.